Imagine that you are pressing on your dresser, sliding it across the floor. You will be object A and the dresser is object B. You each have a center of mass. And we're going to treat each object as a point particle. Now, you push on the dresser. What arrow should I draw to show that force? Here it is. You exert a rightward force on object B. Newton's third law says you feel a leftward force from the dresser pushing on you. Now, each of you also feels other forces. The dresser feels a vertical force due to gravity and also a normal force. So do you. But you might be asking the question, how do you move forward if you have this leftward force? Well, how does the dresser move forward? Well, there may be friction on the dresser, but that friction would be less than your force, and so the dresser accelerates forward. Likewise, your feet exert a force to the right on your body, which has to overcome that force from the dresser, and that's why you accelerate to the right as well, despite having this leftward force. Here's Newton's third law in more formal language. When two objects interact, they exert forces on each other that are equal in magnitude. This force on object B is equal to this force on object A, and opposite in direction. One is to the right, the other is to the left. These forces do not cancel out because, as you may have noticed, they act on different objects. And when you add the net force on object B, you don't include any of these over here. We only add forces on a single object at a time. Another way to think about Newton's third law is that forces come in pairs. And the way you can think about these pairs is very kind of algorithmic. All right, what are the two objects? Person pushing rightward on dresser. Well, if that force exists, here's what you do. Swap the two objects and then change the direction. Okay, so if person pushes on dresser, then dresser pushes on person. Which way? The opposite direction, to the left. And of course, these two forces have equal magnitude. Let's see another example involving a hammer and a nail. You are going to hit this hammer to the right, and you hit the nail to the right, and the nail drives into the wall. Okay, the two objects are hammer and nail. The hammer obviously pushes the nail to the right. Let's draw that force. And Newton's third law says, if the nail feels the force to the right, then the hammer is pushed equally hard to the left. These are the two objects interacting. They exert equal and opposite forces on each other. Now, we could label these forces, and we could also draw additional forces. Both objects have some vertical forces that cancel out. But look at the nail here. What else does it feel a force from? The wall. Is that force from the wall, which pushes leftward, is it equal in size to the force from the hammer? Shorter? Longer? This force has to be shorter because the nail accelerates to the right. So if you add these two, the net force has to be to the right. What about the hammer? How can the hammer move forward if it feels this leftward force? Well, first of all, you don't need a rightward force to move to the right, but more importantly, my hand is holding the hammer, and my hand exerts a really big rightward force on this hammer. So the force of my hand overcomes the resistance from the nail, and that's why I'm able to drive the hammer to the right, pushing the nail in. You may be wondering where these forces come from, these equal and opposite forces. Ultimately, this is a result of electrical repulsion. Now, I'm simplifying and ignoring any quantum effects or the Pauli exclusion principle, but let's just consider electrons. There are electrons in the hammer, there are electrons in the nail, and those electrons repel each other. And that's the source of this equal but opposite forces. Both electrons are repelled, not just one. And so whenever any two objects interact, or maybe you could say whenever their electrons interact, we have these equal but opposite forces. And it's not just electrical repulsion or electrical attraction which has equal and opposite forces. Magnetic attraction, magnetic repulsion, when you look at nuclear physics, the strong force, the weak force, gravitation, every fundamental force in nature produces two equal forces on both objects. Let's see some more examples of Newton's third law. As a frog swims, it pushes the water to the right, so water pushes left on frog. That's how the frog gets moved forward. The same is true for the eagle flying. As the eagle flies, what two objects are interacting? Well, the wings push down on the air, and so the air pushes up on the wings. Again, air is being pushed down. Because wings push down on air, air pushes up on wings. That's what allows the eagle to fly. You've seen this listed sometimes as every action has an equal and opposite reaction, but we're not going to use that phrasing. Instead, we're going to be more precise, and we're going to use what you saw written down on the slide. The next good example is firing a firearm. So when you fire the firearm, gun pushes bullet to the left, therefore bullet pushes gun to the right. That's why the gun recoils. Now, you may have noticed that even though these forces are the same, the bullet accelerates and speeds up much more, whereas the gun accelerates much less. How can their accelerations be unequal, but the forces are equal? The answer has to do with Newton's second law. Net force is equal to mass times acceleration. So yes, the force is the same, but when we solve and isolate acceleration, force is not the only thing in the equation. The gun has a higher mass and therefore a lower acceleration, because when you're calculating the acceleration of the gun, you have the same numerator, but a larger denominator. Here's one more example. You step off a canoe onto the dock, and as you do, your foot pushes the canoe to the right. That's why the canoe recoils, but the canoe pushes foot to the left. Foot pushes canoe, so canoe pushes foot. Now, this canoe will recoil quite a bit, but if you were stepping off of a giant cruise ship, yes, both objects feel a force, but the cruise ship would recoil far less because its mass is so big. So back on this slide, we can add one more thing, which is to say that while the two objects feel the same force, their acceleration depends on the other forces that act and the object's mass. That's Newton's third law. Thanks for watching this video.